Good afternoon. Yesterday I had a talk about using Ceph behind Apache CloudStack. Today there's a talk going into the networking part where I'll do a showcase on how we use VXLAN with BGP and IPv6 in our network. So let's start again about who I am and what I do. Peter den Hollander, born in the Netherlands, living in the Netherlands, and I would call myself a Ceph, IPv6, and CloudStack guru. I love open source, and my daily job nowadays is head of infrastructure at Total Web Hosting Solutions. PC Extreme used to be my company. It was acquired by TWS in 2018. It's a buy and build strategy where we are acquiring hosting companies throughout Europe. And I run the company called Cloud Infra, which is the internal infrastructure company of TWS. And there we run a Ceph and CloudStack using the KVM hypervisor. A few numbers. Running about 20,000 virtual machines at the moment, a lot of Ceph storage, a lot of memory, and a lot of CPU cores where we run regular web hosting. So you should see the Apache web server a lot, MySQL databases or MariaDB, depending on which one you like, postfix mail servers. We're just handling a lot of domain names and web hosting on this infrastructure. And today's talk is about building your network. So when you're building a CloudStack network, you are usually thinking about VLANs and then separating different tenants into VLANs. But if you want to scale out these networks and make them pretty large, layer 2 becomes difficult. You'll be running into scalability issues and redundancy, and they're pretty intertwined with each other where spanning tree becomes an issue. Making a very robust and redundant layer 2 network, which you can also scale out, is challenging. And you have a limitation on about 4,096 VLANs in such networks. And we've been trying to eliminate layer 2 in our network. We want to go for layer 3 only, because why layer 3? It's just better. It's more flexible, it's more reliable and more scalable. And it's simply just better. And even in smaller networks, a lot of people would say, my network is too small for layer 3, I'll stick with layer 2. Well, no, any modern switch you buy from, let's say, Juniper, Cisco, Arista, or whatever vendor can route layer 3 usually on wire speed. And if you start looking on the internet, you'll see that almost all of the hyperscalers are using layer 3 only networks. For example, Facebook and Cloudflare, they also post a lot of information online about how they built their networks. It's pretty interesting, and I've learned a lot from their posts and their research. And getting all the bits and pieces from those different presentations, you can build a pretty reliable network. And of course, just talking to other engineers, talking to network gurus, and then figuring out, hey, how can we scale this out? Because again, my challenge is scaling out the network and getting the reliability and flexibility in there. So when we build a network right now, it still works in 10 years, and we can keep expanding and expanding the network. Now, in 2018, we initiated a project in our company called Compute 2.0. Our existing cloud deployments were based on layer 2, all basic networking. And again, we have few goals: increasing flexibility, scalability, and we wanted to eliminate layer 2. But as well, we wanted to go to IPv6 only where possible. So this is a philosophy we have inside the company. It's IPv6 and only IPv4 if needed. So my yesterday's talk was about Ceph. Our storage platforms running Ceph are IPv6 only. We do all our management of the hypervisors over IPv6 only. We manage our switches and routers over IPv6. The SNMP monitoring goes over IPv6. So we only tend to use IPv6 in our network and only IPv4 to the end user facing services. And even, for example, our hypervisors, the IPMI or IDRAC, depending on the vendor which we use, is IPv6 only. So, and why IPv6? Why would you use future technologies with the IP protocol from the past? So that's usually my answer. So we have this sticker as well, which we actually have it as a sticker, which we paste on, put on some products which are IPv6, IPv4 only. It's just fun. It's legacy stuff. Now, scaling out a network can be done by using VXLAN, and VXLAN is a overlay network over your existing layer 3 network where Ethernet frames are put into UDP packets. It uses port 4, 7, 8, 9, and you'll just see these UDP packets flowing through the network. And by the way, on my left side, I have my laptop open with the chat and the Q&A. If there's any questions or any comments, do post them in the chat and in the Q&A, and I'll repeat the questions so it's in the recording as well, and I'll get back to it. So we build our network using VXLAN, and you see this in many large deployments where VXLAN is being used. So what is VXLAN? Ethernet packets encapsulated inside UDP. So you can route them through any existing layer 3 network. And if you look at some things like with Docker networks, I think it's called Calico, that's actually VXLAN as well, where it builds a on-the-fly BGP VXLAN network to do overlay over existing IP networks. So your Docker containers think they actually have a local layer 2 network, but it's all being encapsulated inside layer 2. Well, if you want to run VXLAN and have an MTU of 1500 inside your VXLAN network, the underlying network needs to be at least 1580 of the MTU. So we chose to go for 9216. So with that, we can also route jumbo frame packets of 9K inside our VXLAN. And then in VXLAN, it's not that we have VLANs, you have VNIs, that's the virtual network identifier. And you're not limited to 4K, you're limited to 16 million VNIs in one network. So you have much more flexibility with your numbering scheme, which you want to use. By default, VXLAN uses multicast. So the forwarding database, the FDB, containing the MAC address and IP information, would then be broadcasted or actually multicasted to other nodes using multicast. However, multicast has its scalability issues, and it's also difficult to route multicast between different layer 2 segments. So it doesn't really scale. Now, the solution to this is actually using BGP and EVPN in combination with VXLAN. So BGP is being used for exchanging the VNI, IP, and MAC information. Actually, this is done by EVPN using BGP. And we know the border gateway protocol from the internet. Everything on the internet works with BGP. All the autonomous systems on the internet actually talk to each other using BGP. This allows us all to scale out the network pretty large, and we're not using multicast because it doesn't scale what BGP does. There's an interesting blog post, which I linked to here, which has some information. And I do see a question coming in. Rohit asking, do you face any VXLAN scaling issues, especially around multicast announcement and that 40 byte packet overhead? Okay, Rohit, yeah, indeed, the question was answered because we use BGP. Multicast, we use it in a proof of concept setup where we do some testing, where we just didn't bother to set up a BGP, and multicast works fine in a smaller environment, but in a larger environment, we use BGP. No, a bit of from Juniper. So Ethernet VPN is just a way to get layer 2 and inside existing layer 3 networks. We also use VXLAN, for example, to do what we call layer 2 transport between 2 data centers, which is completely outside of our CloudStack scope. We just have some switches which talk PGP to each other, and we just connect 2 ports in 2 different data centers. They think they're, in the same network, but it's all being encapsulated inside VXLAN, routed to a different location. And then it just comes out as regular layer 2 network, all done using EVPN. We would say, this is liquid gold, getting VXLAN, BGP, and EVPN and IPv6 in your network. That makes it a very scalable and future-proof network to build on and to go forward with. If you want to use VXLAN and CloudStack, it has been supported since the 4.12 release. We pushed a couple of commits into CloudStack to polish and improve some things. However, if you want to use BGP and EVPN, you need a modified script of the modify VXLAN.sh. Just download the script from GitHub and put it on your hypervisors using whatever tooling you use. Could be manually. Our case, we use Salt, but it could be Puppet, Ansible. And you also need to run BGP on the host. We use FRR routing, so FR routing for the BGP. This is not managed by CloudStack. So you manually need to manage FRR and the BGP configuration so that it starts transmitting the VNI information from the hypervisor to the rest of the network, so that the rest of the network knows where the MAC address of the VM can be found. And security grouping with VXLAN works as well, and including IPv6 support. So that's what we actually use in our network. When you start building, you need equipment, you need hardware. So when we started building network, we said, okay, we need VXLAN switches, routers which can route these packets. We started looking around, and in the end, we found these Dell switches which have ONI support. ONI is the open network installer environment where you can install your own custom operating system on these switches. You can even install Debian or Ubuntu or CentOS if you like, but the main thing is that you need to talk to the Broadcom chipset, and that's why we use Cumulus Linux. That's a Debian-based environment. I'll get to Cumulus in a moment, but it supports and it programs for us the chipset. And we call these our cloud core routers. They are the IPv4 and IPv6 gateways for the VMs. They talk BGP to the upstream network. In our case, that's the autonomous system 48635. And using the 100 gig ports, they have downstream connections to the racks containing our hypervisors. And we also have some 40 gig connections going to the storage racks, which is in our case Ceph. So you'll see these switches connected with all kinds of 100 gig links and 40 gig links going downwards to hypervisors and storage. And I do see Maurice asking a question saying, is it supported with all hypervisors? I know it is supported with KVM. I honestly don't know if it's supported with a different hypervisor. I haven't looked into that. So I can't answer the question. And I see Rohit already answering the question. Cumulus Linux itself is a Debian-based operating system for ONI switches, and it has support for VXLAN, BGP, EVPN, and many other things, but those are the things which we focused on. And you can run your own scripting and tooling. So we run the salt minion to provision the switches, but we also run a Zabbix agent to do monitoring, and we have some custom scripts on there, which we use to monitor and modify these switches. I do have to add that it was acquired by NVIDIA in 2020, and NVIDIA also owns Mellanox, and that means that after version 4.2 from Cumulus, the Broadcom chipsets are no longer supported. Mellanox and Broadcom, you know, they're in a war. They're really competitive with each other, and yeah, starting with the 4.3, you need to have a Mellanox chipset inside your switch. We're not there yet. We're still on 4.1 on most of the environment. So yeah, it's not our problem right now. We need to look at it into the future. But our hypervisor connected somewhere as well. And we also use a Dell switch, which in this case has 48, 25 gig ports, again, Atom CPU, 4 gigs of memory, two per rack, IBGP between the hosts, between the routers, and they talk BGP to the hypervisors. Each hypervisor has a 25 gig to each top of rack switch. That means that they have 50 gig of total capacity. But we also use a smart convention inside the rack. So if the hypervisor is on unit 38, it will be connected to port 38 in that rack as well. Pretty easy for us to identify. So if the hypervisor on unit 38, it's going to be connected to port 38. Very easy for the data center guys to do the network cabling. And it saves us a lot of administration. The hypervisors themselves are either Supermicro or Dell's, pretty much the same setup, depending on the vendor. It's a dual EPYC 64 core, 1 terabyte of memory, a bunch of NVMe's for local storage, because in addition to Ceph, we also use local storage, and they have a Mellanox card in them because it has a VXLAN offloading support. So the card does the encapsulation and decapsulation of the packets, so the CPUs don't need to do this, and they are way faster. So if you want to use VXLAN, always use a card which has offloading. In our case, we're using Mellanox, but Intel and Broadcom have their cards as well, which do offloading. We can fit around 11 to 12 hypervisors in one rack. Although the racks themselves are 47 units high, we have a power restriction. And with these CPUs and this amount of memory, it's 11 to 12 hypervisors, and then we're consuming 6 kilowatts of power in that rack. And so then we need to go to a next rack. So this is how a typical rack would look like. In this case, it's Dell machines in there. So we use cabling, blue and red cabling, to identify the different power circuits. And then you see the 25 gig connections using the direct copper connections. And then there's also one cable for the IPMI. Now, we're talking a lot about hardware, but how do we actually configure this on our hosts? So each hypervisor runs BGP on the host. FRR daemon again running on the host. There's no LACP, no bonding, no teaming. That means there's no layer 2 connections between the hosts. So of course they have a layer 2 between the host and the top of rack, but that's it. And so we're not using ECMP. ECMP is a BGP balancing. We didn't implement it yet because we don't need it yet. However, all the hosts, they announce their IPv4 and IPv6 local loopback addresses through BGP. So they're announcing a /32 in case of IPv4 and a /128 in case of IPv6. Jumbo frames enabled again MTU to 92.16 so that we can forward these large packets over the network. On a hypervisor, this is not the full configuration. I kept out some parts, but this is the most important part, where we see that on the interface, on the loopback interface, we add an IPv6 and an IPv4 address. And then we, the hypervisor themselves, it has a internal autonomous system number, in this case, 4, 2, and then the rest of the numbers. And then it announces its loopback address of both IPv4 and IPv6. And then we have 2 uplinks. So you see the 2 network cards in this case, which are in the pair group called uplinks, and that's what we use to talk BGP to the rest of the network. Those of you working with BGP might say, hey, I'm missing the interconnect subnet between the hypervisor and the top of rack. How is that being done? Well, I'll get to that in a moment. On the loopback, if you go to an hypervisor, you'll see that it has a 10.255 address and a IPv6 address, both set to the loopback interface, which we then announce. Uplink interfaces as well. So you see the 2 interfaces, which are the 25 gig interfaces. They are sending out, they're using for the BGP towards the top of rack. They also have an IPv6 address, which you see that's only being used for bootstrapping the hypervisor. When running in production, everything goes on over link local, and that 2A05 address is not being used. You also see it's being set to deprecated, and we're not routing any traffic over it. But we are using BGP unnumbered. And this is pretty fancy and interesting, is that using IPv6 link local, the hosts and the top of rack, they establish a BGP connection using IPv6 router advertisements. It's being done ad hoc. So they notice a router advertisement from each other, and then they just establish a BGP connection with each other. And that saves you a lot of time of setting up interconnect subnets between the racks, between the top of rack routers and the hosts. So no need to manually assign addresses. That makes it super easy to scale. We use BGP unnumbered between the hosts and the top of rack, but also between the top of rack and the cloud core routers and going from there. Saves us a tremendous amount of time of assigning addresses and interconnect subnets. So in this case, you'll see a route table on the hypervisors where it has a default IPv4 gateway for CloudBridge 1, which is its internal network for the live migration and other stuff. I'll get to that in a moment. And then we see that it learns the link local addresses as routes for the 10.255 IPs where it needs to connect to. So these are different routers and different hosts sending out our /32 routes. So we learn routes individually for each different hypervisor and rack. If we go to a hypervisor in this case, you see a show BGP summary, and it has 2 neighbors where it's connected to over its uplink interfaces. So it has an IPv4 neighbor, an IPv6 neighbor, and then it has an L2 VPN, EVPN neighbor as well. In this case, a 1 pair group with 2 peers and have been connected for 3 weeks and 5 days right now. Now, CloudBridge 1 is the internal CloudStack network. It's VXLAN as well, but it's an IPv4 only network. Currently with CloudStack, it just uses IPv4 only for this internal network. We didn't really bother to go into this yet because we don't have any IP address problems. We're using a /20 in this case. So for the live migration between the hypervisors themselves, we use an IPv4 only. That's live migration, secondary storage traffic, other things which go over there, but it is encapsulated inside VXLAN. We do this using systemd. So you see that we have a VXLAN 200 in this case. So the ID of the VXLAN is 200. We set it to the local IPv4 address of the hypervisor. And then we simply build a bridge where CloudBridge 1 is then attached to VXLAN 200 in one bridge, and we suddenly can forward traffic between the hypervisors, and they can also reach the management server, because the management server lives somewhere else, and I'll keep that out of scope for now, but it's also connected to this VXLAN network living somewhere in that data center, where then the management server and the secondary storage server can connect to all the hypervisors in a separated layer 2 network, although that layer 2 network is encapsulated inside VXLAN. And those of you noticing is that indeed the underlay network under VXLAN is IPv4 only at the moment, because the Broadcom chipset in these switches does not support IPv6 as an underlay network for VXLAN. So we're using RFC 1918 addresses, and in the future it will be supported by these chipsets, but at the maybe the Mellanox chipsets, I don't know. We haven't really put a lot of time in it because we didn't really need it. Our main focus is that we manage the hypervisors over IPv6. We can do so because they are advertising their loopback address /128 route, which we use for management. IPMI is all IPv6 only. The Ceph traffic is IPv6 only. So only the VXLAN traffic inside the data center goes over these IPv4 addresses. A drawing, which some of you have seen yesterday as well, but this time we're going to be focusing on the left side where it says CloudStack KVM hypervisor. This is one of the deployments which we have in Amsterdam. And you'll see that you have two top of rack routers, which are interconnected using 2 times 100 gigabit. Then we have the hypervisors connected using 2 times 25, and those are connected in this case to router 138A16, and on the right side, B16, which are these cloud core routers, which have their 100 gig connections going towards the hypervisors and the 40 gig connections going towards one of the Ceph clusters. And the actual traffic towards the internet is being done using Juniper network routers, the MX240 and MX960, depending on the data center location. These do not forward VXLAN, so the VXLAN is terminated when I go back at the routers 138A16 and B16. They do talk BGP upwards towards the Juniper MX960, but they are not doing any VXLAN anymore. So all the VXLAN stays, let's say, below in this drawing, and it doesn't go outside this network at the moment. We are using unique VNI numbers in our different deployments so that we can interconnect them if we would like to, but at the moment we're not doing that. Now, one of the deployments in Amsterdam, so we have in this case 9 racks, 6 racks with hypervisors and 3 racks with Ceph storage. And as you can see, we have 12 terabytes in most of the racks of memory, and 2 racks are still filling up. So they need to have some more machines going in there. And this is something you would not be able to achieve using just layer 2, because there are so many hypervisors and VMs in here. With layer 2 spanning tree, it would be very challenging to build this out and keep scaling it out. You need to have a leaf spine situation. I wouldn't want to do this with the amount of virtual networks which we have as well. Now, you would say that they are pushing quite some traffic. They can. I took a screenshot of today. In the night, they sometimes might be pushing 100 gigs or more. This is just to illustrate that they can push enough traffic. So these are the Dell switches with the 32 times 100 gig ports, and they're forwarding at max 40 gigs in the night with probably backup traffic going to the outside world. But usually web hosting itself doesn't do that much traffic, although it's a lot of packets per second. We don't do that much traffic. We're not a streaming party where we do video streaming, for example. So the amount of bandwidth which we do is not that insane. And these peaks are just backup traffic. But so how do we then configure the gateways on the cloud core routers? Well, if you log into Cumulus Linux, you'll just find it's a Debian CLI, which you get. So in the network interfaces file, we, in this case, it's called VLAN 624. It's a bit of a Cumulus Linux thing. I have a few links in later in the presentation. And then you see that it has an address, and then there's a virtual address as well, which is the virtual IPv4 gateway. And with IPv6, we configure this inside the FRR routing, where it starts sending out router advertisements. So there's no virtual gateway for IPv6 because both routers are sending out their router advertisements, which then are being learned by the VMs as gateways, so they can forward their IPv6 traffic. So in CloudStack, for example, we have a bunch of networks. I skipped the names of the networks on the left and a few tenant things, but you'll see that we have, this is just a summary of some networks in one of the CloudStack management servers, where you see a bunch of different IPv4 and IPv6 address subnets being connected to these networks. And there could be hundreds or thousands of VMs inside these networks in total. I see that there's a question if we are using some security hardware, firewalls, IPS in your topology. Yes and no. So if you look at our network, and I'll go back to this drawing here, at the top you see that there's the Juniper MX routers, and then there's even the core IP network, AES48635. There is S-Flow running in that network, which is just doing sampling of all the traffic. And if we see traffic going over certain limits, and I'm going to be a bit skeptical about sketchy about this, because I don't want to give out all the information how we do this. But we do with S-Flow, we track traffic flows, and if traffic becomes suspicious, we send it to a inspection machine, some IPS and some firewalls, which do additional filtering on the traffic before it's then being sent down back again to the routers and then goes towards the network, rest of the network. So there is firewalls and IPS, but that's completely outside CloudStack and happening on a different level of the network. So if we want to scale this out, you can see we could scale this out to a large amount of racks pretty easily. With VLANs, we had to be conservative. We don't want to use the same VLAN number or the same VNI, even if it's a different data center again, because it might confuse people. So all the VNIs which we use are unique. And as I said, in the future, we can then also connect the different networks to each other, different data centers to each other. But right now they're completely isolated. But we can provide isolated networks for customers on request. So that's what we see here. We have all these different networks in CloudStack, which are just routing different traffic. So we don't have networks with multiple IP ranges in there. So there's always going to be one IPv4 and one IPv6 subnet in each network. And then we simply create a new network in CloudStack. And we can keep adding racks with hypervisors and storage as we like. We have enough data center space available, and I just ordered an additional 40 hypervisors, so they're on their way. Ordered more Ceph storage, more routers, and we'll just keep installing the same racks with hypervisors, the same racks with storage, and keep scaling it out. And if we run into issues where the Broadcom chipset can't learn more routes or more layer 2 neighbors, we can simply add more cloud core routers in this case, and then simply shift some workload of the gateways to different cloud core routers while we don't need to change anything. We just establish a few more BGP connections between the routers and top of racks, and we simply can forward the traffic. Let me go to the Q&A because I see a question coming in. Do you use advanced zone with security groups or without security groups? That's a way asking that. A combination. So if I would go back to this network, this overview, most of the networks are actually security groups because there are VMs in there which we cannot trust completely. So I want to have the security groups enabled so it does filtering of MAC addresses, IP spoofing is prevented. We do have a few networks where we have security groups turned off, but that's only for tenants which we know we can trust, or we manage the VMs ourselves. And why would we turn off the security grouping? Sometimes we use floating IP. So we simply say CloudStack cannot use a certain part of the IP space, and we can then float these IPv4 addresses or IPv6 addresses between different nodes without CloudStack knowing it. So that could be pretty easy using HA proxy with VRRP inside the VMs. But most of the time, security groups are turned on. And I see another question. I'll get to that in a moment. So as I said, with scaling, we can simply keep adding more hypervisor racks, more storage, and more cloud core routers as we like. This actually brings me to the end with a few links. So I recommend that you want to learn something, start reading these. Facebook has some very interesting papers on how they built their network using BGP. Scaleway has something about their VXLAN as well. Interesting blog post, and NVIDIA from Cumulus Linux has interesting information on how they build this. And I do see that Venko has a question. Do you use unique BGP ASN on each hypervisor and BGP router? And do you have an IBGP? And do you use some other internal routing protocol for the underlay network? Okay, let me get to that question, and I need to go to this drawing again. So what you see here on the left down side, you see the KVM hypervisors where it has the two Cumulus Linux routers. So this is Tor 138A05. They have an IBGP connection. So they have the same autonomous system. Each hypervisor has its own autonomous system number. So we have the top of rack forms one IBGP connection using one ASN. And then each hypervisor is a unique AS. The same goes for the cloud core routers. In this case, we have two. They have a IBGP connection and they form a internal autonomous system as well. And each rack, so then if we add a new rack, the top of rack has a unique AS, and then all the hypervisors have a unique AS. And that's why we're using the long AS numbers. So we're not starting at 65,000, we're using the 4.2 million AS numbers. So we have enough AS numbers in our network available. And no, we don't use any other internal routing than BGP. So there's no OSPF or something. And I do see I am actually running out of time right now. So are there any other questions remaining?
I think that's it, Guido. Brilliant.
Yeah.
Thank you. That concludes the Guido track at the CloudStack Collaboration Conference.
Indeed, it does. It does. So if you have any questions, please send them to me. I would actually love that you send them to the user mailing list or the dev mailing list. So it's not a one-on-one traffic. It goes to the mailing list, and then other people can learn this and they can find it on Google at a later point. So I prefer sending it to the user mailing list, and you can CC me in the email. That's just fine. But I'd rather have everybody reading the email than just a single person.
Brilliant. Thank you, Guido. And last thing, just to say, everybody, please give Guido a big virtual round of applause. Thank you, Guido.